This is the full solution to the 2009 AP Chemistry Exam Form B. You should go to the AP Chemistry website at collegeboard.com to download and print a copy of the exam to use with this video. 1a. To calculate the concentration, we need the number of moles and volume. The molar mass of C2H5NH2 is 2 times 12.01 for carbon, plus 7 times 1.008 for hydrogen, plus 14.01 for nitrogen, equals 45.09 grams. The number of moles is the mass divided by the molar mass. The concentration is the number of moles divided by the volume, which is 0.500 liter. B. The chemical equation is given. The equilibrium constant Kb is the C2H5NH3 plus concentration times the OH minus concentration divided by the C2H5NH2 concentration. Water does not enter the Kb expression because it is practically a pure liquid. C. The problem tells you that C2H5NH2 is a weak base. When a weak base dissolves in water, most of it should remain unprotonated, so the C2H5NH2 concentration should be much bigger than its protonated form C2H5NH3+. D. 1. The pH and pOH of any aqueous solution must add up to 14, so the pOH is 14 minus the pH. The OH concentration is 10 to the negative pOH, which comes up to be 8.5 times 10 to the minus 4 molar. Two. HCl is a strong acid, and it dissociates completely in water to give H plus and Cl minus. The H plus should protonate the base C2H5NH2, giving H plus plus C2H5NH2 going to C2H5NH3 plus. Three. H plus is a strong acid, and its reaction with C2H5NH2 should essentially goes to completion. So this is just a stoichiometric calculation. The number of moles of H plus is the volume multiplied by its concentration equals 0.100. The number of moles of the other reactant C2H5NH2 is 0.250. Because the stoichiometry is 1 to 1, H plus is the limiting reagent and it controls the number of moles of products formed. The number of moles of C2H5NH3 plus formed is 0.100 mole. The total volume is the sum of the two equals 1.000 liter. Therefore, the concentration of C2H5NH3 plus is 0.100 mole divided by 1 liter equals 0.100 molar. To calculate the value of Kb, we have the values of OH minus concentration from part 1 and the C2H5NH3 plus concentration from part 3. So we will need the concentration of C2H5NH2. From the reaction, the number of moles of C2H5NH2 left is 0.250 mole minus 0.100 equals 0.150 mole. The concentration is the number of moles divided by the total volume equals 0.150 molar. Putting these into the Kb expression, we get Kb equals 5.7 times 10 to the minus 4. (2a) In the experiment, the initial concentration of S2032- is varied and the initial rate is measured, so the S2032- concentration is the independent variable. (b) This is a first-order reaction because the rate increases linearly with the concentration of S2032-, so the rate is K multiplied by the S2032- concentration to the first power. Notice that the rate constant K is just the slope of the linear equation in the graph. C. To compute the value of K, we can use any one of the experiments. Using trial 1, we get rate 0.020 molar per second equals K multiplied by the concentration 0.050 molar. So K equals 0.40 second to the minus 1. D. For a first-order reaction, the concentration of the reactant depends on time through the integrated rate law, log of the concentration at time t divided by concentration at time 0 equals minus kT. We put in the concentrations and solve for t, and t comes out to be 4.0 seconds. At a lower temperature, the rate constant K usually decreases. Since the rate is equal to K times the initial concentration, for every concentration in the experiment, the rate is now lower. In addition, the slope of the graph should also be smaller, so the graph at lower temperatures should look like this. (3a) If a closed container contains water, the water always evaporates and leaves a small vapor pressure in the gas above it. So the total pressure of the gas is the partial pressure of the O2 produced plus the vapor pressure of water. The problem says that the water level is the same inside and outside, so the total pressure must equal to the outside pressure. The outside pressure is given as 762.6 torrs. The vapor pressure of water is given as 21.6 torrs. So the partial pressure of O2 is 741.0 torrs. B. The number of moles of O2 is given by the ideal gas law. We have to convert torrs to atmospheres. And then Celsius temperature to kelvins by adding 273.15. N comes up to be 7.304 times 10 to the minus 3 moles. C. The mass of H2O2 decomposed is related to the number of moles of O2 produced by stoichiometry. H2O2 and O2 have the stoichiometric ratio 2 to 1. The number of moles of H2O2 reacted should be equal to the number of moles of O2 produced multiplied by 2 divided by 1, which equals 14.61 times 10 to the minus 3. The molar mass of H2O2 is 2 times 1.008 for H plus 2 times 16.00 for O equals to 34.02 grams. The mass of H2O2 is therefore 0.4969 grams. D. The problem says the H2O2 solution has a total mass of 6.951 grams. So the mass percentage of H2O2 is its mass divided by the total mass times 100%. E. In H2O2, each H atom has oxidation number +1, but the compound is neutral and the total oxidation numbers must add up to 0, so each O must have oxidation number -1. O2 is neutral, each O atom must have an oxidation number 0. F. We know H2O2 goes to O2, and during this process the oxidation number of each O atom goes from -1 to 0. In doing this, 2 electrons must be produced. In water, H plus or OH minus are available for us to balance the charge of any half reaction, so we can add 2H plus to the right. (4A1) Barium nitrate is soluble. It gives barium 2 plus and nitrate NO3 minus in solution. Potassium fluoride is also soluble. It gives K plus and F minus. When these are mixed, a precipitate forms. This must be BaF2 because the other possibility, KNO3, is soluble. So the reaction is Ba2 plus 2F minus going to BaF2 solid. 2. Because the stoichiometry is 2 moles of F minus to 1 mole of Ba2 plus, if you have equal number of moles of F minus and Ba2 plus, F minus will be the limiting reagent. B1. The problem tells you that cadmium is oxidized. You can look up the reduction half reaction in the table and see that the oxidized form of cadmium is cadmium 2 plus, so cadmium goes to Cd2 plus 2 electrons. Cu2 plus should be reduced to Cu metal, so the balanced equation is Cd plus Cu2 plus going to Cd2 plus Cu. 2. Number 1, we should see that the cadmium metal dissolves as Cd2 plus goes into the solution, and Cu metal should be formed on the surface of the cadmium. The Cu2 plus ion has a blue color in solution. As the Cu2 plus is reacted away, its blue color should disappear. C1. The ionic compound sodium sulfide contains Na plus ions and S2 minus ions. The S2 minus is a weak base and is protonated by water to form H2S. But Na2S is not soluble, so the balanced equation should have Na2S but not S2 minus. The equation is Na2S solid plus 2H2O going to 2Na plus H2S plus 2OH minus. 2. S2 minus is the conjugate base of the weak acid H2S, so a solution of S2 minus is weakly basic and the pH should be greater than 7. 5a. The Lewis structure of N2 is this. And for NH3 it is B. The delta G0 per mole of the reaction is minus 34 kilojoules. We need to calculate how many moles of the reaction has occurred. The molar mass of H2 is 2 times 1.008 equals 2.016 grams. The number of moles of H2 used is mass divided by molar mass, equals 5.95 moles. Every mole of reaction uses 3 moles of H2, so the delta G0 is the number of moles of H2 divided by 3 multiplied by negative 34 kilojoules equals minus 68 kilojoules. C. When all the bonds are broken, the reactant molecules are broken up into their atoms. When the same happens to the products, you get exactly the same atoms. You know the reaction is exothermic, so the bond dissociation energies of all the products are higher than the reactants. D. The balanced equation is N2 plus 3H2 going to 2NH3. On the reactant side, you have 4 moles of gases total. On the product side, you only have 2 moles. So the entropy should decrease. E1. The relationship between delta G, delta H, and delta S is delta G0 equals delta H0 minus T times delta S0. From above, we know delta H0 is negative. We also know delta S0 is negative. But the absolute temperature T is never less than 0. So at low temperature, the second term becomes small, and delta G0 takes on the sign of delta H0, which is negative. At high T, the second term dominates, and delta G0 takes on the sign of negative T times delta S0, which overall is positive. You know delta G0 is negative at 298 K, so at some higher temperature, delta G0 must change sign and become positive. 2. At low T, delta G0 becomes more negative and the reaction should be more spontaneous. At low P, the equilibrium shifts to the side with more gases, so pressure should be kept high to increase the yield. 6a. We are told that the reaction between TL plus and Ag is non-spontaneous. But when a cell is connected, a reaction does occur, so the spontaneous reaction should be the reverse, and TL should go to TL plus plus an electron, and Ag plus should go back to Ag, which is the reduction reaction. B. The overall reaction is TL plus Ag plus going to Ag plus TL. The anode is where the oxidation half reaction occurs, which is TL going to TL plus plus an electron. This is the cell on the left. D. Electrons should flow from the anode to the cathode. And we need to put the salt bridge back in to complete the circuit. E. The overall cell potential is the reduction potential of Ag plus minus the reduction potential of TL plus. You can look up the reduction potential of Ag plus from the table. Just solve for the reduction potential of TL plus using the known overall cell potential. F. We are given the reduction potential of PT2 plus. You can look up the reduction potentials of nickel 2 plus and Ag plus in the table, and we list them in increasing order. So if we combine the platinum 2 plus reduction with the oxidation of nickel to nickel 2 plus, we should get the largest overall cell potential. And this comes up to be 1.45 volts. G. The question is whether platinum will react with Ag plus spontaneously. For this to occur, the reaction is the overall cell potential is the reduction potential of Ag plus minus the reduction potential of PT2 plus. and this comes out to be less than 0. So the reaction is not spontaneous.